welcome back. We talked about flow coloring duality in plane graphs last time, and this inspired Bill Tutte to propose a couple of conjectures whose aim, I think, was to somehow divorce the main coloring theorems for planar graphs from planarity, from topology altogether, and come up with some combinatorial conditions that imply this kind of colorability, be it 4 or 5 or 3 or whatever colorable, that plane graphs exhibit, but not for reasons of being plane graphs or planar graphs, but for some other reasons which he wants to identify in these conjectures. So I'm going to tell you about those today, but we'll start with an obvious conjecture once you have worked out in the exercise classes that every graph does indeed have a k-flow for some k. We can ask what is the smallest such k if there is one for all graphs. Is there a universal bound? Is there a k such that all graphs have a k-flow? And if so, how small is it? And Tutte's answer to that is, I hope it's going to be 5. Right? He didn't prove that, he conjectured that, but that's one of the most fundamental and famous conjectures in graph theory altogether. So the 5-flow conjecture, Tutte's 5-flow conjecture, says that every bridgeless, obviously, graph has a 5-flow. Right? And that is true for planar graphs. Why is it true for planar graphs? Well, if your graph is planar, you can look at the dual, and in order for it to have a 5-flow, you need to prove that the dual can be colored with 5 colors. And maybe you've heard that it can. So that's the 5-color theorem. Which tells us that every graph that can be drawn in the plane can be colored with 5 colors, vertex colored with 5 colors. Right, so that's the 5-flow conjecture generalizes that to arbitrary graphs which need not be planar. Of course, you all know that every planar graph can be 4-colored, also they say, and then one might ask, well, why 5 in the flow conjecture? Might it not be true that every bridgeless graph even has a 4-flow? And that would be really nice. So that would detopologize the 4-color theorem. Right? If we could prove that every graph has a 4-flow, then, well, if it's planar, we can, if given any planar graph can be 4-colored, yes, we can. Just consider its dual. It has a 4-flow, and therefore, by the constructive proof that we had last time, we can 4-color it. So that would be really, really cool. It has a slight drawback, and that is simply that it's not true. So here's the Petersen graph. Petersen was a Danish mathematician. You can read about him in the notes about 100 years ago. So Petersen came up with this graph. Watch as I draw it, because then you remember what it looks like. If you just take the picture, it's much harder to remember. So you remember this, and now the rest is easy, but looks complicated. Right, so this is the Petersen graph. It has 10 vertices. And it's cubic. So having a 4 flows equivalent to admitting a 3-edge coloring. And you can sit down and play with it for a week or 5 and then prove that it doesn't have a 3-edge coloring or equivalently that it doesn't have a four-flow. So unfortunately, that prospective strengthening of the five-flow conjecture to a four-flow conjecture saying that every graph has a four-flow is not true. Right, but something else might be true, and that is indeed known as the four-flow conjecture, also by Tutte. And it says that every graph, well, that doesn't have the Petersen graph, that doesn't contain the Petersen graph, has a four-flow. Right, that makes utter sense if I say it the way I have just done. And the only reason it makes sense is that I'm glossing over the question of what does contain mean. Right, the four-flow conjecture says that every bridgeless graph that doesn't contain the Petersen graph as a minor has a four-flow. And excluding it as a minor is a pretty strong way of excluding things. Excluding it as a subgraph, topological minor even, or a subgraph, or even an induced subgraph, makes much fewer demands on the class of graphs that are still allowed, but excluding something as a minor is a much more sweeping exclusion. And so the statement that a bridgeless graph that doesn't contain Petersen as a minor is a much weaker statement than, say, the statement that every graph not containing it as a induced subgraph, say, has a four-flow. All the same, it still implies the four-color theorem. Right? Give yourself a planar graph, then look at its dual, that's its plane dual, that's a planar graph. That doesn't contain the Petersen graph as a minor because that's not planar. And you can sort of check that by Kuratowski or whatever way you like. By the four-flow conjecture as Tutte proposed it, that dual, which doesn't contain a Petersen minor, would have a four-flow, and therefore your graph that you started with would have a four-coloring. So it's much weaker than excluding the Petersen graph or some other graphs by way of a stronger containment relation than minors, but it's still strong enough to imply the four-color theorem, and of course it follows from the four-color theorem for planar graphs. Right, so another way of phrasing that excluding the Petersen graph as a minor is a rather sweeping exclusion is to say that the graphs that do admit a four-flow is not closed under taking minors. Right? If you have a graph that has a four-flow and you take some arbitrary minor, that needn't have a four-flow. If it always did, if it was closed under excluding minors, then there'd be a characterization of that graph by forbidding excluding minors. We'll get back to that later in the course. So, but it is not closed under taking minors, and can you think of a graph that has a four-flow and yet also has the Petersen graph as a minor? It's not hard. Just think of the arsenal of examples that we have. Can you think of a graph that contains the Petersen graph as a minor and has a two-flow? The answer is yes, you can. So please do. Which graphs have two flows? How about K11? All degrees even? Right? So K11 has more than 10 vertices, and it contains the Petersen graph as a subgraph even. and therefore also as a minor. Okay, so the class of graphs that admit a four-flow is not closed under taking minors, so this statement of the four-flow conjecture is a little unmotivated perhaps, but it's still a strong statement, strong enough to imply the four-color theorem. Okay, and then there's also a three-flow conjecture. So let me introduce that as the analog of the three-coloring theorem for planar graphs. What's that? It says it's a theorem due to Grötsch, and it says that every planar graph that doesn't contain a triangle can be three-colored. All right? So not having a triangle translates for the dual into not having a cut consisting of exactly three edges. So the three-flow conjecture says that a graph that doesn't have a cut consisting of exactly one edge, a bridge, which it mustn't have in order to have any flow, and doesn't have a cut consisting of exactly three edges, has a three-flow. And that's also open. Right, questions about these flow conjectures? No? Okay, then I'll show you a proof of the best theorem that's known in this area, and that's due to Paul Seymour. He proved that every graph, bridgeless of course, has a six-flow, so just one short of the five-flow conjecture. Okay, and on that's theorem 661. Let me give you a proof of that. And the proof that I'm going to show you is due to Matt DeVos and Catherine Nurse. It appeared just last summer on the archive, so that's a relatively new and very pretty proof. The original proof is in the 5th edition of the book. Okay, and it's going to be an induction proof. Every bridgeless graph has a sixth flow, is the statement of the theorem. And we're going to prove something more. For every graph G, bridgeless, and for every vertex that we can choose in that graph, there exists a Z2 by Z3 flow on G. Right, that's this group that we had a variant of last time. So it has 6 elements, so that's fine. And it suffices to prove that there is an H flow for any abelian group H of order 6. And now there's an additional condition such that F, let me give it a name. So F, and I write that as the product of F2 and F3. These are the component functions. So for every edge, you get an element in Z2 and another element of Z3, and these are given to you by F2 and F3 respectively. Right? So that's one function assigning to every oriented edge an element of this group, which is a pair, first component of which is assigned by the function F2, second by F3. So there will be such a flow on G such that F2 is 0 on all edges incident with U. That's the statement we're going to prove. So it's the original statement, remember that G is bridgeless. With this additional condition thrown in. Okay, so let me prove that by induction on the order of G. On the order of G, and it starts at K1. Right, for K1 there's nothing to prove. It has the required flow because it doesn't have any edges, so to every edge you can assign whatever. Right, so the induction starts easily, and for the induction step, we may assume that G is two connected. Right, why? If it isn't two connected, we can prove it has the required flow separately on every component to start with. Well, let me do it in one sweep. On every block. We can prove it separately on every block. We have a little U that's given to us that lies in some of the blocks, maybe in several if it's a cut vertex. But in whichever block it lies, we can apply the induction hypothesis to that block and get the required flow for that block with respect to this little U, if indeed it lies in that block. If not, we just pick any old U. So on every block, we get such a flow, then we just put them all together to get a flow for G. Right, so that's easy. Axiom F1 is obviously satisfied because it just speaks about individual edges. And axiom F2 says that at every vertex, the sum of all the flows into that vertex is 0. Well, it lies in several blocks, and the edges around it are partitioned into those from the various blocks. And for each partition class, the sum of those values all into that vertex is 0. So we sum over a few zeros to get 0 on every vertex, even a cut vertex, when we put those flows together. So we may assume that G is two connected. So let's look at G minus U. U is this special vertex here that's given to us. And the first case is that G minus U has a bridge. Call it E. Okay, so here's our U. And G minus U has a bridge that's a cut consisting of one vertex. So G minus U is connected because G is two connected. And if it has a bridge, then it has, that bridge separates it into two connected sides. Let's call these sides V1 and V2. And if we add little u to Vi, then we'll call that Ui. So we have U1 and U2 consisting of one side of this cut of G minus U given by the bridge E plus the vertex U itself. So U1 and U2 intersect exactly on U. Well, now we apply the induction hypothesis apply for both i's, 1 and 2. The induction hypothesis to GI, which is G in which we contract UI. Right, so G1 is obtained from G by contracting the entire set V1 and U. So U sends at least one edge to each of the VI, because if it didn't, then G would not be two connected, right? If you, say, didn't send an edge to V2, then E would separate V2 from U. That is not going to be the case. So U sends edges to both VI, and so to get G1, we contract all the edges that U sends to V1 and any edges inside V1 as well. And for G2, we do the same here. So each time we get a smaller graph. And to apply the induction hypothesis, we have to, well, is it bridgeless? Yes, it is bridgeless. Whenever you contract something in a graph, you don't create a bridge. So that's useful to remember. It is bridgeless, and in order to apply the induction hypothesis, we're allowed to give ourselves a little u, and the little u we're giving ourselves is the contracted vertex. So we apply the induction hypothesis to this with special vertex V ui, which we might call little ui. So that's our standard notation for the contracted vertex arising from contracting the connected set ui. Right, so that gives us a flow, Z2 times Z3 flow on the green graph and on the blue graph, on G1 and on G2, whose Z2 component is 0 at the special vertex. Okay, so the edges on which these two flows take their values are almost exactly the green edges, or the blue edges and the green edges respectively. If we contract this, then all the edges that we have to assign a value to are the remaining blue edges and E. And similarly, if we contract blue, then the edges that we're assigning values to are the green edges and E. So let's throw these two flows together. Let's take as the desired function here whatever the appropriate function from the induction hypothesis assigns to a green or a blue edge. And on E, we have to make up our minds. And since we are always bad at choosing things, and like to avoid having to make choices, we say, oh, well, never mind. We just adjust one of them, one of the induction hypothesis flows, so as to agree with the other one on E in F3. Right? F2 assigns 0 to both of them. Right? Because E is always incident with the contracted vertex. So we're fine on F2. F3, we have two versions from the induction hypothesis, but we can just invert the Z3 component of one of them to make it equal on E, on both orientations of E, to the value of the other one, if it isn't already equal to that, right? So if for G1 we get, say, value 1 mod 3, and for G2 we get 2 mod 3. Well, 2 mod 3 is the same as minus 1 mod 3. So by replacing that F3 for the second induction hypothesis flow with its negative, we turn the minus 1 or the 2 into a 1, so it agrees with the value of the first. And then we're done. Questions about this case? No. Right. Good. Yeah, it's easy. Okay. So case 2. Well, case 2 is that G minus U does not have a bridge. And then G minus U is 2-edge connected, because by assumption it's connected. G is 2 connected, so G minus U is connected. And connected and bridgeless implies 2-edge connected. So we know that G minus U is 2-edge connected. Okay, so choose neighbors X and Y of our little u in G minus U. X and Y. Why does U send 2 edges across? Well, because G is 2 connected. Okay, and then between these two neighbors, X and Y, we use the 2-edge connectedness of G minus U to join them by 2-edge connected paths. Okay, and we give the union of these two paths a name and call that union H. So H is an even degree subgraph of G minus U. Okay, so next thing we do is we contract H So this U might have some more vertices, more neighbors somewhere here. Right, I just picked two special neighbors. It might have some more. We contract H now. So all the edges that U sent to H will become edges from U to this new contracted vertex, which I think I'll call U1. Yep. U1 had better be a green vertex. So that's little U1, and the other neighbors remain where they were. We'll call this graph G1. And now we pick one of these edges from U to H, say the edge to Y. Call that E1, and we contract E1. Contract E1. Now, we have this vertex, the contracted vertex here. Let me give that the name of U2. And the other edges that were there in G1 between U and U1, so for example, this edge here, they're still there. They're there as loops. And these edges here are also still there. Right. Okay, so that's G2. And now we apply induction. First, we work our way backwards. We start with this. We apply induction on G2. G2 is genuinely smaller because we contracted something. And as before, contracting edges doesn't create bridges, so it's smaller, it's bridgeless. So we can apply the induction hypothesis with special vertex U2. Apply the induction hypothesis to G2 with U2. Okay. That yields a flow with values in this group. Let's call it F2, F3, upper index 2, referring to the G2 here. And this will be such that the values of the first component at U2 are going to be 0. So F2 up to will assign 0 to these edges here to the blue edge. And if we look at those same edges here, it will assign 0 to these three edges here. It can't assign anything to E1 because E1 no longer exists here. Right? But it will give all the edges at U value 0. All the edges at U, except E1, which no longer exists, will get value 0 under the first component of this flow on G2. Okay. Now we want to move that flow back to G1. And remember, we had this lemma 613, which said that if we have an H flow on a graph obtained from our favorite graph by contracting an edge, then that can be extended, as we said, to the original graph, and it will, so that it becomes a flow there with respect to the same abelian group, except that on the uncontracted edge, it may be 0. So once more, this flow here gives us a circulation on G1 with values in the same group as before, with the property that all the values on edges other than E1 are going to be non-zero. Does the blue edge have a value? Yes, it does. It does if we use the proof that I gave you for 613. It doesn't have an unambiguous value because here it was a loop. So a loop does get a value in a flow, and it must get a non-zero value in the flow. But then when we want to define or shift this flow interpreted as a circulation on the uncontracted graph, we have to make up our minds whether to assign the value that this flow received here to this orientation or to that orientation. Do whatever you like, but make one choice for every loop. And then, no matter how you made that choice, one has to compute the value of that flow on E1 accordingly, as we did in the proof of 613. But then there will be one unique value that makes it into a flow, into a circulation. This circulation may have value 0 on E1, so that may happen here as well. This flow here defines a circulation here that's non-zero everywhere except possibly on E1. If it is 0 on E1, we can use a little trick. We just use at its second component, this one here, that will also assign 0 to E1. The 0 in our group is the pair 0, 0 in Z2 and Z3, right? So this will also assign 0 to E1. And it will assign something non-zero to the blue edge. And there exists a blue edge because you sent at least 2 vertices to G minus U, and those we called X and Y, and they are on H because that's how H got defined. So the blue edge does exist. There may be another edge. And now we look at F3 up 2, which unfortunately is 0 in E1, and it has some value on the blue edge. Indeed, it has value 1 in Z3 in one of the 2 directions. It has 1 in one direction and 2 in the other direction, because 2 is minus 1. So let's assume it has value 1 in this direction here, 1 in Z3. But now we can simply add a little circular flow of value 1 to our F3 up 2, namely replace this 1 with a 2 and this 0 with a 1 in this direction. Right? And that doesn't change axiom F2 because in equals out. We're just doing that locally on the F3 component of the flow that we have. So now we have not only a circulation on G1, but indeed a flow. And does it satisfy a requirement that at U1, the F2 component should assign a value 0? Yes, it does, because the edges incident with U1 were all incident with U2 here, all they didn't exist and were E1. So E1 gets value 0 under the first component here automatically, because there's no other way of giving it a first value. Why not? Because all the other edges at U1 sum to 0, because here they're incident with U2. So E1 must sum to 0 too when we build our unique circulation in uncontracting the edge. Okay, so F2 is already 0 on E1, and it's 0 on all the other edges at U2, at U1, because they're edges at U2 here. So this gets a little 0, this gets a little 0, these get zeros, and so on. Okay, so we have found a flow F2 up 1 and F3 up 1 on G1 with special vertex U1. Well, that's good news. So let's do it again. And obtain from this flow here a flow here with special vertex U. And the way we do that is simply uncontract all the edges of H one by one, if you like, or all at once, it doesn't matter. And then using lemma 613 again. We've got our Z2 by Z3 flow on G2. Then we apply lemma 613 just to the Z3 part of that to get a Z3 circulation on here that is non-zero everywhere except possibly on the contracted edge E1 that was contracted to form E2. And then we modify that using the fact that there's another edge between U and U1 than E1. We modify that in such a way that it's non-zero also on E1. So we have a Z3 flow on G1. Then we use the lemma again, 613, to expand that to a Z3 circulation here that's non-zero everywhere, except possibly on the edges of H that got contracted to form G1 from G. So that's the Z3 part. And the F2 part is much simpler. We just steal the F2 part from here. So that assigns values 0 or 1 in Z2 to every edge other than E1 and other than those in H. And we just copy those values all the way directly to G. Now that gives us a circulation on, sorry, we didn't have a flow, we had a circulation. Similarly for Z3, we earlier had a circulation here. And we copy the values of the Z2 part all the way to here to get a circulation, a Z2 circulation on all the edges except E1, right? Because E1 didn't get a value here. That's fine. And then we use that and just add values 1 along the edges of H. So before we add this, the sum of the outgoing flow at every vertex of this Z2 part is 0, because it's the same sum that we computed here. right? The vertices not incident with H, I mean, they have the correct sum, they satisfy axiom F2. And how about the vertices that are incident with H? Well, their values are all 0 here, because these same edges are incident with U2 here. So their sum is simply 0. And when we add to every such vertex a 1 in and a 1 out, it remains 0. So that's fine. And the edges incident with U, their axiom F2 is also satisfied because all the edges incident with U are 0 over there.